So first of
Oh,
all, welcome everyone today. We really appreciate from different corners of the world, I imagine, and across different time zones. And I imagine we all three, the presenter at the moment, you see, we are all spread across different time zones. So that's really fantastic. And we sincerely thank you for joining us this early or this late, depending upon where you are. So on that note, I would like you to welcome again to the what is first joint webinar between the EAGE and EAG, two European societies. And our speaker today is Eric Oelkers. And for people who have interest in geochemistry or some sort of geochemical affiliation, Eric is quite a familiar name, I imagine. But I have like few points ahead of me which I'll quickly go over. For example, Eric is co-founder of Carbofix, and is globally recognized for his contribution to carbon capture and storage technologies. He has held several academic appointments in the past, including at a professorship at the University College London, research directorship at CNRS France, and adjunct professor at University of Iceland. He is also the former president of the European Association of He is co-founder of Chemical Perspectives and Geochemical Perspective. And I've been fortunate enough to meet Eric in person. I'm not sure if he remembers at different Goldschmidt conferences over the years. And one of the things I really enjoy when I interact with him is his passion for science and the way he communicates with a wider audience. So that is something that I found remarkable and something which I'm really envious of Eric. So I think with that humble introduction, the floor is all your, Eric. Please take over from here. Thank you.
wow, thank you. That was probably more than I deserved, but I appreciated it anyway. Good morning, everybody, and thank you all for joining us today. And particularly since I've got and giving me this opportunity to talk about one of my favorite subjects, mineral carbonation, particularly as a way of storing carbon dioxide, removing it from the atmosphere, and putting it safely in minerals. Now, I would hope that everybody, imagine everyone here, unless you're living under a rock or have completely shut off all electronic communication for the last several years, understand, know, and appreciate the need to limit the amount of CO2 in the atmosphere and the likely need or desire to develop successful carbon capture and storage techniques. So I'm not going to start there, but I really want to do is start with an overview of the big global problem facing us in terms of carbon capture and storage. I'll do that with my first slide. Assuming that it goes, sorry about this. Next, that works. We'll see if it works. I'm a little bit weary on all this, but let's go it this way. Here we go. I've got two pictures next to each other. The top are, as you read here, the global fossil fuel CO2 emissions. And the important point is it's going up, it's still going up, and we're somewhere around, round number, I'll say 40 gigatons of CO2 a year going into our atmosphere. So that's about 40 gigatons. That's with a big G. And down here, which is, because I got it from the web, not the best picture necessarily, because the scale is a little bit difficult to read. But here in red is the global CO2 storage as a function of time from 2010 to 2021. And we see here it's somewhat less than 40 million tons of CO2 being captured and stored annually. So up on top here, we've got about 40 gigatons, big G, 40 megatons, not gigatons here of global storage. So if you, this is not working as I'd hoped to. Sorry about a minute. Okay, there we go. So we got 40 gigatons emitted, about 40 megatons captured and stored. You do the math, only about 0.1% of the emitted CO2 is being captured and stored globally. That isn't much. But wait, the problem is even worse than that. Because of this 40 megatons being captured and stored, roughly 90% of it is being used for enhanced oil recovery. And I could spend an hour talking about advanced oil recovery, but just in summary, advanced oil recovery, every time you do a full life cycle analysis of it, it emits more CO2 to the atmosphere than you actually put into the ground. So this is, I think, not very well understood. I think people have been misled. Point is, it's in carbon storage. It's almost really CO2 enhanced petroleum to a degree. So if you remove that, less than 0.01 all CO2 being emitted to the atmosphere is being captured and stored at present. This is a shockingly small number and needs to be moved up. One of the things that I think is going to help move it up is that, in fact, there now seems to be a financial incentive to help store carbon. And some of it's shown here. This is the European EC trading scheme. Over the last cost for buying carbon offsets on the open ECU trading market. And we see here, and I'm abandoning the cursor because it doesn't seem to be compatible with the system that we're working on here, but we're upwards of about 80, as of last week, about $80 a ton. So if you succeed in storing carbon and you can sell the offsets, you can get 80 euros a ton of money. Well, basically, you can make a profit on it potentially because you get about $80 a ton coming back out of it. So one of the ways that can be done to address carbon capture and storage is mineral storage. It's something I've been involved in quite a number of years. And I want to introduce it with the aid of the next slide here. And I've got probably a somewhat out of focus picture of what I use sometimes to introduce the carbon cycle. Basically, in simple terms, CO2 dissolves into rainwater as the rain falls. That CO2 acid, it dissolves calcium-bearing silicates largely on the surface of the planet, liberating calcium and bicarbonate, and makes some clays as well. This makes a lot of our soils on the Earth's continents. The calcium and the bicarbonate go into the ocean, where eventually they precipitate as calcite and sink into the subsurface. Eventually the CO2 will come back into the atmosphere and volcanoes, but that's a process that typically takes hundreds of millions of years. In simpler terms, that chemistry is shown here. CO2 dissolves in water. Carbonic acid promotes the dissolution of silicate rocks. In this case, I wrote it to diopside. And that liberates the calcium and bicarbonate into the solution, combined to get calcium carbonate. They make a carbonate mineral, and that completes the carbonation process. And the beauty of this process is, particularly for us who try to do mineral carbonation, is these reactions go chemically downhill. Everything in life, as a thermodynamicist as I am, things go downhill. For example, here's anorthite, one of my favorite minerals, hopefully one of yours. It's the calcium end member of plagioclase. If it reacts with 400 ppm CO2 in the atmosphere, plus some water at 25 degrees, you can make calcite and kaolinite, and you actually even get 36.3 kilocalories per mole for every mole of CO2 that you take out of the atmosphere. It's fabulous. So not only do you get carbonation, but it goes energetically downhill. Similarly, for people who prefer ultramafic minerals, here's phosphorite. Phosphorite plus atmospheric CO2 at 25 degrees can make you magnesite, and in this case, amorphous silica, and gives you back 23 mole. In fact, it's quite a nice process here. We go through the whole thing, we carbonate, and we actually get energy. This is minerals want to do. Well, if they have, and we can make them do it. And we do see these sort of processes all around us when we look around. One example I have shown here, this is a actually very, very glassy basalt hand sample that I picked up in Western Saudi Arabia about a year or so ago. And we see here a lot of white minerals on top of that glass, some of which, not all of which, are calcite. It's a number of other evaporite minerals, because here in Saudi Arabia, we rain, it evaporates a lot, and we're left with some of these residual evaporite minerals on the surface. More commonly, such as you see here. I like this picture a lot. I was on a field trip in southern Australia just before COVID struck, and I'm pointing out a bunch of wonderful looking carbonate veins in I think this is an ultramafic rock, if I recall correctly, here on the south coast of Australia. We see this around. It's energetically favorable. The world does this by itself. So this has motivated us to try to use these natural processes to capture and store CO2. Now, there's two ways of using these processes, either on the surface of the earth, and that's called ex-situ, and in the interior of the earth, which is in-situ carbonation. And I'm going to, over the next, hopefully, half hour or so, go through what I see as the current state of the art of both of these potential technologies. First, ex-situ mineralization. And here, a slide that's a sort of nice little schematics, Grant, and you could read along with me here. Ex-situ carbonation or enhanced weathering, sometimes you hear it called enhanced weathering, but basically minerals that naturally absorb, I would say, who would carbonate precipitation. So it's a little bit misinterpreted, perhaps, in this slide. But the idea is you take minerals that will dissolve and promote carbonation, you crush them really small, you spread them on fields, you dump them in the oceans, and the hope is that this increased surface area will help those silicate minerals dissolve more rapidly and accelerate the formation of these stable carbonate minerals, locking that CO2 into these stable minerals where they could last stably for millions of years. Now, the low-lying fruit, or the lowest lying fruit for ex-situ carbonation, actually is mine waste, because this stuff, mine waste, is already naturally crushed and exists. And I just want to introduce it briefly with the next slide. And this is, I don't want to go through details in this slide. I steal a lot of slides from the web, just because people on the web and web designers are much better at making cool looking pictures than I can. But the basic idea is to take and try to manipulate or engineer the crushed waste from different mines. There's a lot of mines around the world, and use that to try to use them to accelerate the carbonation of CO2 in those minerals by somehow with reaction with this mine waste. And so this is some examples that I've taken from, well, I think the pictures came from the web, but the text is mine. If you look at most mine sites, and this is very promising, when you look at them pretty carefully, the major carbonation of these mine waste is not actually silicate minerals, but it's this mineral called brucite, which you've got up there in the magnesium hydroxide mineral. So it's not generally the carbonates, because in fact, carbonate dissolution, even when you still keep things crushed, tends to be fairly slow. So brucite tends to carbonate, but olivine and other products really don't tend to. And the brucite, I just pointed out just below, is that the second line below, the brucite itself is actually a product of high temperature alteration of the olivine by the reaction I showed below, olivine making brucite plus serpentine. And the serpentine is actually fairly unreactive. So it turns out that these mine wastes, although they are promising, it's not simple to make this go. And it's not clear, at least to me, that we can even make most of the silicate rocks in those things carbonate. The jury is still very much out on this. The other challenge, which I'm not going to go into very deeply, is that the brucite itself carbonates fast and tends to make an impermeable crust on top of these waste piles, making it a challenge to get the CO2 deeper into the structure of any sort of waste pile. But though that we do certainly see carbonation of brucite and perhaps some silicate minerals to a degree in these, but that's still a challenge. One of the on this, and people tend to be really somewhat going to be very excited about. And you go onto the web and you get sort of text like this. They estimate annual potential of as on the order of 100 million tons of CO2 stored a year this way. And if you go through, and this is on a recent paper that I grabbed this text, tailings contain high abundances of olivine, serpentine, diopside, and they show the highest potential due to their favorable kinetics. I think the important word here is potential, because it's not really clear that we know how to do this. In part because, and some of which I'll go into, is first of all, these reactions are somewhat sluggish, even when you grind the material. And in addition, these minerals and these reactions on the surface like to do other things than just make CO2. I mean, when I look around at ultramafic rocks on the Earth's surface, I really only know of, or really could think of, and maybe you guys out there have some new ideas and better ideas, but I could really think of two places on the surface of the Earth where something like olivine, serpentine, or diopside actually carbonate. And I'm just going to share them with you in the next two slides. Oh, okay. First, actually, where does olivine actually promote carbonation? One is alkaline lakes. A couple of years ago, with a couple of my colleagues in Toulouse, we looked at the chemical processes in one of these alkaline lakes called Lake Salda, and I've got a picture of it there for you. In that case, it's very particular environment. There's drainage from a ultramafic rock into a closed basin, but the secret here is that once that closed basin, so there's a lot of evaporation going on, but the real key is that in this lake, there's a whole huge amount of cyanobacteria. Cyanobacteria, think about that green sludge on your swimming pool or the local lakes. That's your cyanobacteria. Photosynthesis itself raises up pH quite impressively, and this then provokes the precipitation of carbonate minerals. One of the reasons why these carbonate minerals are magnesite is difficult to carbonate is, in fact, magnesite doesn't like, or is kinetically inhibited to precipitate at low temperatures. To carbonate olivine and these other magnesium silicates at ambient temperatures, you seem to have to go all the way to precipitating hydromagnesite, or these even more obscure magnesium carbonate minerals called nesquehonite and diponite, which are far less stable than magnesite, so need a bigger push to get them to go out and precipitate in natural systems. The second place where olivine could promote carbonate is potentially in seawater, but the tricky part here is when you combine olivine or magnesium silicates in the ocean with seawater, you don't actually make magnesium carbonates, but you provoke calcium carbonate or aragonite precipitation through the alkalinity obtained by the dissolution of the magnesium silicates. And this idea itself is being promoted as well as an idea, surface carbonation. And this is largely championed by the Vesta. Sure, other people are doing it. The idea is you grind up olivine really fine, you throw it in seawater, and basically you cross your fingers hoping that it does the right reaction. One of the big challenges is once that olivine is put in seawater, it's very difficult, if not too impossible, to know what happens to the reaction products of that. And of course, Vesta's gotten several million, certainly, being invested into all this. So at least investors think that there's something to it. But the challenge here is, and this is the chemical reaction. I'm not going to go through it. There's apparently this is videotape, so look through these reactions, and this scheme they hope is going to happen. CO2 is going to dissolve into the ocean, which I believe does happen. It's going to react with the olivine, the alkalinity, which will, for some reason, in their scheme, calcite and silicates. The real challenge, and again, I'll leave this, you can look into all this if you want. I stole it, I think, from the Vesta website. The problem is that it's not clear what olivine is going to make in the ocean. If olivine just dissolves and makes alkalinity and adds bicarbonate ions to the ocean, you'll get 4 moles of CO2 for each mole of phosphorite you toss in the ocean. That would be pretty good. I mean, it's very difficult to imagine that one adds material to the ocean and one merely increases, however, the dissolved mass in the ocean's been around for millions and billions of years. And as a result, it's pretty close to steady state in the composite elements, just at least on a small scale. So it's much more likely that olivine will provoke some calcite precipitation and perhaps amorphous silica, and maybe to a degree, the magnesium concentration that goes up. If that happens, and if you're lucky enough that happens, you'll get rid of and consume 2 moles of CO2 per each mole of phosphorite. But actually, if you leave this stuff long enough, and these are experiments we've done in the lab, you leave long enough, you actually get magnesium clays. Light is a common magnesium clay. And when you start making the magnesium clays, the precipitation of magnesium clays gives back the proton that you dissolve in the phosphorite in the first place, and you get no moles of CO2 per each mole of phosphorite you put in the ocean. And depending on which one happens, you may get carbonation on the surface, you may not. And this points out the biggest probably challenge in mineral carbonation today is actually inventorying what happens, what reactions happen. Because of course, these mineral carbonation reactions do go down energetically downhill, but depending on what you make, it's not the only reaction that goes energetically downhill. The making of clays from these silicates go energetically downhill. There's lots of choices for those reaction products. If you make the right one, you carbonate. If you make the wrong one, you've wasted. Okay, so in order to address that sort of, a couple of companies are doing this. I'm working right now with a 2.0 where, this is a group that I've enjoyed, and they've to a waste, and for the last month, and this is the Royal Week because I had COVID last month and couldn't help making the pools myself. We're actually setting up a number of closed pools and seawater, and we are monitoring pools to verify what's the fate of the dissolved olivine, and so we know how much we could stop the reaction to optimize the amount of CO2 that the olivine is sucking out of the ocean. And the future, of course, then for us, at least working in CO2 zero, is designing some large-scale lagoons where we can do a bit better controlling what reactions between our olivine and our seawater. Another alternative that people is adding dust to soils. And I know this is, I think, a very intriguing idea. I know even more than 20 years ago when I was visiting family in Chico, California, the local agricultural supply store was actually selling bags of ground basalt as fertilizer for your farms. The trouble is, again, a question of inventory. You add basalt to soils, you can actually, it's great nutrients for the soil. It could draw down CO2, but to date, the studies are completely inconclusive because the trick is, happened. How do you know how much carbon's been drawn down? How do you measure that? These are complex systems. One of the quotes that I got actually off of the Drawdown Initiative website from apparently one of their geologists, after 1 year, like I did on the completion of my PhD, I know how and how much more complex it's assumed. So that off the web is the state of the art. It's being tried, but right now, despite all the brouhaha, there's really not much proof or quantification at all. We really don't know how much CO2 most of these systems are actually drawing down. Nevertheless, If it is, it's not clear to me personally what the scale of this sort of thing can be. The surface of the Earth has limited space. It's not clear to me how much enhanced weathering is possible. I should point out on this regard, and maybe I'm talking when I get on all this, but we have to keep in mind that all the weathering of the surface of the planet brings down no more than about 0.2 gigatons of CO2 per year. I personally cannot imagine increasing global weathering of the Earth's planet of the surface by factors of 2, 5. If you want to get a gigaton, we're talking about increasing that by at least a factor of 5. I can't imagine increasing the global weathering of the planet without other consequences. That you just can't manipulate the Earth that much without something else getting a little bit out of whack. So I would say, just in terms of ex-situ mineralization, I think it'll make many people money, and a large amount of venture capitalist money is being poured into it. I'm not sure in it itself is going to be at a scale that's going to be in terms of solving carbon capture and storage. It will contribute, it'll make people money, but getting the scale up is going to be a very, very big challenge. An alternative to this, which is much more difficult to get going because structure, involves in-situ carbonation. I love this picture mostly because I'm in the picture with, of course, Ziggy G, who's there, looking very sharp and black, but also great being there. But also I'm with Wally Broker, who sometimes was called the father of global warming, a title that he hated. And in the center, looking very sharp, is Olof Grimsson, who was the president of Iceland at the time. And this is a picture when we started CarbFix back. The picture's from 2009, but we started this in 2006. So this idea was we were brought together by the Icelandic president to try to find a solution for CO2 in Iceland. And because they don't have traditional hydrocarbon reservoirs, really the only solution was to put the CO2 into basaltic rock, and try to carbonate it. Now, the idea is fairly simple. We take CO2, we add it to water, we inject it into the basalts. Fairly simple. The original CarbFix took place here. This is in front of us is a headless area power plant. Over in green in the distance was our original CarbFix injection site. And we started developing this. This took us from 2006 to the first test 2012. We're talking about 6 years of time to develop the technology, and with a lot of mistakes along the way, which I'm not going to share with you today. The subsurface and the scheme looks like this, and you've probably seen some of this before already. This is the subsurface. We have an injection well in the center. And let's see here, we pumped 1 to 3 kilograms per second of water into the subsurface, along with CO2. And we also put in, and this is very critical, we put in at the same proportion of CO2, non-reactive tracers, and also in this case, radioactive carbon. And this is very important because it allows us to inventory and determine quantitatively how much of the injected carbon was actually fixed in the ground. This is critical to any sort of carbon storage. The validation is absolutely essential. Then water was put in again with the tracers, and we pumped water out of a nearby monitoring well at 2 kilograms per to pull the flow towards us so we could actually see what the fate of the CO2 was that we injected. Just for all of you to see it, this is an old picture. Some of you may have seen it before. This is what the original CO2 injection well, CarbFix injection well, looked like. For all of you that thought it was really cool and all that, basically wells are just a hole in the ground. And here are some of our students at the time, including in the corner, there's Sandra, who is one of the chiefs of the ongoing CarbFix operation in Iceland today. So we also had to design a special injection system. In this case, we injected CO2 as small bubbles in downflowing water and they dissolved before they went into the formation. Anyway, this is all published, so you can look at the details in some of our papers if you are so inclined. But basically, the key was here, and I've got two pictures here where we did the mass balance. Based on the non-reactive tracers, we could calculate how much, in the top figure, for example, dissolved inorganic carbon in our water samples if there was no chemical reaction versus what we actually measured in carbon in the water. And from this, we concluded quite happily that pretty much at 25 or 35 degrees in that system, more than 95% of the CO2 we injected had precipitated in the subsurface as stable carbonate minerals. And this then, for us, we were quite excited. We had pictures like this that we published at the time. Actually go from, instead of here on my left-hand side, taking years and years to wait till the CO2 is safely stored in minerals, we could do it in, well, really in less than a year or two. We could actually take our CO2 all the way from being gaseous CO2 to having tons and tons of this stored in stable minerals in the subsurface. We then collectively upscaled this and what we refer to as CarbFix2, industrial scale up. In this case, we actually took the water from the power plant. We captured the CO2 by putting it into a scrubbing tower, which is basically just this big shower, and then injected that water. And well, big shower at pressure. We inject that water directly into the ground without separating the CO2 at all or depressurizing it. And this is actually a very cheap way of capturing CO2. And some of the work we indicated, and so long as the CO2 stream is more than about 10% CO2, this winds up being cheaper than most of the alternatives for CO2 capture. And again, this is the overview of the site. This is the tiny little bit next to the sort of near the, well, you see let's see in the lower corner, the headless area power plant. This is a deeper system. The blue well, HN16, is our injection well. And those orange wells, which are diverted, which is why those lines are there. The dots show where the well is, the lines show where they're diverted to, are various monitoring wells where we could watch and assess the fate of the injected CO2. The system in the subsurface looks like this: injection, flow, monitoring wells. And for all of you that haven't been there already, this is what the injection well of the current CarbFix system looks like. CO2's being brought into this system. This is now a higher temperature system and being injected into the subsurface. And there's Yngve on the side, one of the engineers that worked with us on this project at the time. But that's what it looks like. It looks great, but it's a bit noisy in there. What you don't miss is the noise and such. And that's what it looks like on an industrial scale. And again, just like in CarbFix 1, we did the conservative tracers and non-reactive tracers, and we used those, in fact, to demonstrate that the majority of our dissolved carbon, and in this case also, a lot of the financial motor for this was getting rid of the hydrogen sulfide. Almost all of the hydrogen sulfide was fixed in stable minerals within months of its injection. So at an industrial scale, this seems to work very successfully, and it's still ongoing today as pretty much the only real subsurface mineral storage system right now that's working today. The point is also what makes this also attractive, it's fairly cheap. This whole system, ongoing system at Headless Area, the costs are sort of listed here, but it's costing approximately $25 a ton to capture, transport, and store hydrogen sulfide and CO2 at Headless Area. And this compares, I say here, to what's listed as conventional CCS. I'm not know if I really believe that $30 to $110 a ton number, but that's what was kicked around when the slide was made. But certainly it's significantly cheaper than the conventional cost in this case for capturing and storing hydrogen sulfide, which is on the order of $300 a ton. So our collaborators, Reykjavik Energy, has saved a fortune and are saving a fortune every year by taking this mineralization approach versus capturing and storing just hydrogen sulfide using the conventional approach. So this is in order to be able to really assess whether or not this is an approach that could be generalized to other sites, we really have to consider and make estimates of how much CO2 can we actually store in the subsurface. And that's a very difficult thing to do. Our approach was first, and I'll go back to the slide that I was showing here before, that we started to look at natural analogs. And what I show here, and this is a rather complicated picture, but this is basically color contour plots, which is B and C on your picture, of the amount of CO2 that is we see naturally stored based on the mineral composition of a large number of drill holes located in the western part of Iceland. And we can see here that, let's see if I got, right here, we see from about 50 to 100 kilograms per meter cubed of CO2 is stored as calcite in these rocks. We see also here that it's limited to the top about 500 meters of, and that's because CO2 carbonation is only thermodynamically favorable at temperatures less than about 250 degrees. CO2 becomes unstable at high temperatures. And these are geothermal systems. That's why the drill holes are there. And so the calcite's all limited to the part of the system that is no deeper than no hotter than about 250 degrees. So we take this information and we go around the world. There's a large number of places where there are basalts, some fresh, some less fresh, all around the world. And we take that number and we've identified the largest sites around the world, and they're all listed here. I'm not going to go through all of them, but there's some of them on a table here, and you look at them. Some places that are obvious, the Rift Zone in Africa, Ethiopia, the Deccan Traps in India. Right now, we are looking and investigating projects right now in India, in the Arabian Peninsula, and of course, Iceland still. And the important point here is you see that each of these sites, even the Iceland, which is relatively small on this list, we estimate that there's at least 2,000 gigatons of storage potential available. This is huge. This, just Iceland alone, that's, to me, if I do that division in my head, that's probably 50 years worth of global storage can be done in Iceland alone if this was upscaled. All done relatively inexpensively and all fairly safely, relatively safe, because we're putting the CO2 into stable long-term minerals. Stable minerals, the average residence time of these carbonate minerals in the earth is somewhere around 200 million years. So once we make it there, this is about the most secure storage we're going to find, and there's plenty of space to do it. Also, I should point out is that peridotite, carbonate peridotite, this is being pursued right now by a company called 4401, based largely in Oman. Okay, the other issue now for upscaling, and what I think is exciting, is that this sort of storage can be upscaled. We can start with a few wells, and if it's geothermal wells, these things are relatively cheap wells, maybe 1 or 2 million euros. It may sound expensive to an academic person, but this is fairly cheap for wells, because compared to oil wells, they don't have to support very high pressures. And one can build a whole suite of shallow wells, which will limit the cost of any one well or the risk of any one well clogging. This idea is now being pursued by Carbfix, which is spun off as a company, something they call the Coda terminal. The trick in Iceland is there's not that much CO2 around to store. So the idea here is that CO2 is going to be shipped on boats to the Coda terminal, where it's going to be injected with water into the ground. And I was a bit skeptical at first, but I pulled off just recently the numbers off their website. And Their estimate is that the total upfront investment cost, and you can see it here, is going to be somewhere about 250 million euros. But when you take into account how much CO2 they're going to store, as well as the transport, they get the total cost of transport and storage they estimate is going to be somewhere in the order of 50 euro a ton range. And as you recall, the European trading scheme is getting you about 80 euros a ton. So this is going to make money if it all goes as planned. Their goal right now is about 500,000 tons of CO2 per year, starting about 2026, and upscaling with several ships to 3 million tons a year in 2032. This is a very promising and exciting potential where one can use the basalts and the huge storage potential of these basalts to store large amount of CO2 from around the world. Now, one of the things that I think is particularly exciting is the idea of air capture with mineral storage. And this has been done also. We've done this collectively with CarbFix in collaboration with a company called Climeworks. And here's a wonderful picture on a beautiful, clear day of the Orca air capture plant located right next to the Headless Area Power Plant. This, however, I should point out, I mean, I'm a little bit mitigated or I have my reservations about this particular technology. This whole plant, which is quite impressive and fairly large, captures all of about 4,000 tons of CO2 per year through an amide capture technique. And right now, it's at least $600 a ton per CO2 stored. So I really have to wonder if that's a particularly good value and if this is really the low-cost technology that's going to be embraced in the future. Okay, despite that, I should say this, despite this, Climeworks has used this and leveraged this into such great publicity. They've managed to raise, at least if I understand correctly, hundreds of millions of dollars in venture capital. So maybe this isn't the technology, I'll just buy out somebody else that has different technology that's cheaper. I do think that the cheapest technology, and what I find most exciting, is actually something called mineral cycling for capturing CO2 directly from air. And CO2 cycling is a very, 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 very old idea. And I mean, I actually probably, and you, maybe all of you in the audience, probably, or many of you in the audience, knew about this years ago. You just didn't think about it this way. And I just give you where I've probably first came in touch with it. And this comes from Tom Sawyer. And I don't know about you, but I had to read Tom Sawyer by Mark Twain when I was in junior high school. And one of the most famous instances or parts of this is a whitewashing the fence. Tom Sawyer, sort of pictured here, is there busily whitewashing a fence. And well, what is whitewashing? What you do is you take some calcium hydroxide, lime, you pour it into water, you mix it up, you paint it on your fence. And actually, I've done this on the ceiling of my country house, and it actually does very nicely. You spray it on. The CO2 gets sucked right out of the atmosphere into the strong basic solution, reacts with that calcium, and makes a thin coat of calcite, and that's whitewash. It's just like making Portland cement. This is capturing CO2 direct from the atmosphere. And the thing is, if you merely heat it up, you can separate the calcium oxide and the CO2 again. You can use that pure CO2 stream and store it. And you've got your lime all over again to keep going through. And thermodynamically, I just pulled this out to show you. Basically, you're playing off of the thermodynamic curve. This is for magnesite and periclase. But at low temperatures, the carbonate's stable. At high temperatures, these minerals decarbonate. If you merely heat this stuff in a closed kiln, like we use to make cement, you can capture a pure CO2 stream. And if I understand correctly, you just go back and forth and back and forth and back and forth. Through this, you can capture a pure CO2 stream. And again, if I understand this making cement correctly, it costs no more. You can buy cement for no more than about $50 to $100 a ton. So the technology to do this on a big scale and fairly cheaply is already there. And this has been pursued by a number of organizations as well, including, for example, Carbon Engineering and Heirloom. I just put them there as exception. And this picture here is one that I dragged over their website. It's being engineered right now. I think this promises to be able to air capture at least no more than about $50 a ton once it's all optimized. I think this is a very promising solution to air capture, elegant and simple. And of course, I like it in particular because it involves mineral reactions. And it's great to see mineral reactions helping out and helping us solve world problems. So that's where I am. I'll just summarize some of my major points in my last slide. And I'm sorry to have this all written down, but basically what I've got here is what I think is the state of the land right now. First, ex-situ carbonation is very, very challenging right now because we haven't successfully verified most of these surface ex-situ carbonation schemes. I think, reasonably we might be able to expect to capture and store upwards of 100 million tons annually. This won't solve the world's problems. It'll make some people probably very comfortably off financially because, there's a lot of revenue in that. And it will contribute, but it's not going to, I can't imagine it being the scale that would work to have a really large impact on that 40 gigatons of CO2 being put in the atmosphere today. In-situ carbonation, I think, actually has a large amount of potential because it's safer, cost-effective, and the volume is very high. And it looks like a number of efforts are going on, and I'm involved in a number of efforts right now to try to apply this to different places in the world. And finally, my guess at carbon is that this particularly will work best if we can couple it with air capture. And I find that mineral cycling is probably right now holds really good promise to provide this at a low cost. So hopefully I haven't put you all to sleep. I can't see you. Here, I'm really talking at my computer screen, so I hope some of you are still out there. But now that thank you very much for all of you who've stayed. And I'm looking forward to questions or comments, and if we don't get through all of them now, you can always send them by email. Thank you very much. And I'm going to shut off the talk because then I can see you, because I could see nobody while I was giving that talk. Oh, I didn't do too bad. I did it in almost 45 minutes.
Exactly. Thank you, Eric. That was really a wonderful talk. And I think I was
you.
really sort of like impressed by the fact that you managed to condense all the ex-situ technologies and the in-situ technology. And some of it, honestly, I had no idea existed in the real world. And there was so much capital behind these technologies. So there's quite a bit of
huge money
progress.
flowing into all this right
Yeah,
now.
exactly.
But actually, I find, and this is, it's going to sound bad, but most of these startup companies, and there are a huge number of startup companies, I get calls all the time from startup companies. I've been asked to start up companies myself by venture capitalists. What's surprising is, if you look, most of these companies are 3/4 management and publicity people, and a small 1 or 2 bits of science stuck on the side. I find it shocking. I find it shocking. So, I mean, it seems like the big issue on most of these right now is people sniff money. And it's more, and sorry, maybe I'm going to offend some people. For a lot of these people, they're selling a fantasy, but they're pretty successful at selling a
I might
fantasy.
pause you there, Eric, for a minute and ask the audience if they have any questions before we stop
And
streaming.
true, stop me before I offend everybody in the audience.
No, that's all good. Thank you, Eric. So please feel
I
free
can,
to yeah, I think Marge, you can take over from here. Thank you.
yeah, I can see some questions. So from Hans, there is a question: what are
Well,
the main challenges to bring mineral cycling to
mineral
scale?
cycling, it's mostly optimizing the engineering. And my understanding is, and I talked to Peter Kellerman a week or two ago, that at least the people in Heirloom apparently have this whole thing optimized. It's not it's not rocket science. I mean, as I said, Tom Sawyer did it back in the 1800s, right? We know how to make Portland cement. You just heat up limestone, you put it on your backyard in a pool of water, you then dry it out, you put the CO2 into a closed kiln, and you get a pure CO2 stream. I don't think there's any challenges on all that. It's just a matter of engineering, and apparently it's already there to a large degree. There's not it's so simple. You and I could do it in our backyard. And that's what I like about it. And as I said, what I also like about it is I know the cement industry sells concrete cement for, well, it's under $25 a ton in some cases. It can be done cheap. We've got Julian. Hey, Julian, who's an old friend of mine. And he's asking, in terms of mineral cycling, extracting the minerals and then carbonating it is generally CO2 negative. Is it energy efficient? I can't tell you the details. I mean, my understanding is it can be, and that's part of the engineering. I mean, ideally, if you, it all depends, of course, you know, one would have to do a life cycle analysis. It all depends, of course, on where you get your heat from, how energy efficient. You are burning your coal to get the heat. It's going to be different than if you're using solar energy to heat, right? So that's really a case-by-case thing, and it gets optimized. Can it be energy? Can it be CO2 negative? Absolutely. I mean, it can be completely, if you use energy that has no, if you use energy that has no carbon footprint, that's easy. But that's you know, that's engineering to a large degree, and but it certainly can be done. I've got K Dang, sorry. Two questions, that's tough. How is the depth of CO2 charged water injection set? Well, that's simple. That one I know how to answer. The key is keeping the CO2 for mineral storage, and what we do, and there's some debate over whether or not you can inject pure CO2 and have it dissolve in water and carbonate in the ground afterwards. But what we do, the essential is that the water has to be injected at a depth such that the water pressure is higher than the CO2 pressure in the water, or else you get bubbles. I wish I had a bottle of Coke and I could show you what happens if the pressure is too low, but you could probably do that experiment in the comfort of your own kitchen. If your pressure is too low, just like when you open up a bottle of pop or a bottle of Perrier, CO2 bubbles out. So you need the depth to be higher than have enough pressure to keep the CO2 into the aqueous phase. For us in headless area and some of the designs that we're working on, we like 25 bars of CO2 pressure because that somewhat optimizes the amount of CO2 you could put into the water. And there you have to go about 25 bars. So you've got to be 25 bars of water head. So you're talking 250 meters worth of water above your head. I mean, we recommend a margin of error, so at least 400 meters. But that itself is not very deep. And the other thing that's important to remember on all this in terms of these water wells is that as opposed to putting CO2, like as a gas, into a subsurface oil field, we don't have to pressurize the water or the gas. You need that head, but if you inject, sorry, you've got a water table here. We're dealing with systems that are hydrostatically pressured. So the wells themselves can merely be water wells. You don't need a big, expensive infrastructure to keep the pressure in. These are merely cheap water wells. You release the CO2 in the water into either deep into that water well, and it'll still flow in by gravity. You don't even have to push it in most cases. Or you could bubble the CO2 bubbles into the water as you're pouring water in, and the CO2 bubbles will be carried down, dissolve as they get carried down, making big energy savings on the storage. Next, two, which part of the world might Carfix be better for, tropical or polar regions? Personally, bias is places where food and wine are good, because if I'm going to set them up, I want to enjoying my time there. And I'm much more of a tropical person than a polar person. The bottom line is it really doesn't make that big a difference, because what I'm going to say is that the temperature gradient in the subsurface is somewhat independent of your air temperature where you're standing. Iceland, one of the coldest places I visit regularly, has some very high thermal gradients. Whereas there, the Gulf Coast of the U.S., where there's a large amount of petroleum, and I sometimes visit my parents, well, my mom who lives on the Gulf Coast. It's really warm. They got a low thermal gradient there, so it's more related to the thermal gradient of the system. As we see in CarbFix, in 2 years we carbonated the CO2 we injected at a depth of about 500 meters, where the temperature was 35 degrees centigrade or something like that. And we've also done it in Iceland, where it's 250 degrees centigrade. So, but it's much, much faster at that temperature, but it works at both temperatures. And once the CO2 is in the ground, you've got time on your hands for those reactions to go. Next. Thank you. Could we go back in history and paint our walls with calcium? Actually, I like that story. Can we actually paint our walls with whitewash our walls? Actually, I like that because it lets me continue a little bit more of my story. You can. There's nothing wrong with it. You can add lime to water, pin it on your walls. I don't know if you'll actually get the volume you need worldwide to do it, but the only thing is wear gloves, because what I learned, of course, is calcium hydroxide's a base. You add CO2 to the water and you start painting on the ceiling. And I did this in our country house. We've got this wonderful 12th to 15th century country house where one of the person recommended that I do this, so it gives it the ancient feel. So I'm there painting the ceilings and all that, and it's all dripping down on my arms. And about halfway through painting the ceiling, I noticed I was getting all up and down my arms, because this stuff is about a pH 13-ish solution. So as a result, that's why in part it sucks out the CO2. So yeah, can we paint walls that way? Sure. The other thing is it doesn't stick as well as modern paints do. So I would say it's not worth the effort. I've gone back now to using regular latex paint on my ceilings because it was a nuisance. Okay, Alyssa asks, I would ask why CO2 shipping is better than transport option using pipelines. It's really a matter of how long the pipeline's got to be and how much the cost is going to be. Right now, people are putting on boats. It's an economic choice, absolutely an economic choice. And right now, it appears that that's the cheaper alternative, basically. Could people do it in pipelines? Sure. People pipe CO2 around somewhat in pipelines. It can be done. It's just a matter of economics. Philip asks, I'm currently involved in enhanced weathering in Brazil, something called Rochecam. Sorry, I have never heard of that, but Roche again, rock dust. Okay. Mostly in terms of food security and health, it's true, especially for the high. So if we could measure the additional CO2 question, basically the question seems to be, do I think it would be a good idea for encouraging farmers to be compensated for the CO2 they sequester to motivate them to use ground rock on their fields to promote both growth and carbonation? The answer is, of course. I mean, the one thing that I find, and I'm working a large amount, more and more with private companies now, you need the carrot and the stick. If you don't actually provide a carrot, people are, sorry, maybe not the group of you that are here in the audience, but the world and businesses out there are greedy. They want to make money. You got to give them a reason to do it. If you can possibly, and we hope we can, and someone can, an inventory and figure out how much CO2 we're actually storing by adding rock dust on grounds. I have heard rumors, by the way, that some of these studies suggest there's actually more CO2 going out than going in by adding rock dust, in part because one's promoting the faster decomposition of the organics in the soils. But I really don't know enough about that to go into very much detail. But inventorying, it's going to be tough. Understanding soil processes, that's not simple. I mean, I would suggest, though, trying to do
did we lost Eric's feed?
I think you lost connection.
Okay.
I think we will wrap after that question, and if Eric can still come in, that would be great. But if not, thank you everyone for joining us in this event. Alok?
Yeah, thank you everyone. Thanks to Eric if he can still hear us. But yeah, thanks everyone. It was great to have you here. And we'll keep
Mhm.
organizing more events down the road. So make sure you follow us on LinkedIn. There we have a separate group on LinkedIn. And we also have the mailing list as well, I imagine, for EAGE. So keep visiting the website and we'll sure to organize more of these events. And I think that'll be all for today. Thank you very
Mhm.
much and see you all in a future event. Thanks.
Thank you.